Today, we're delving into a paper titled Scaling Proprioceptive-Visual Learning with Heterogeneous Pre-trained Transformers. This research tackles a significant challenge in robotics, building generalist robotic models that can adapt to diverse embodiments and tasks. What are the key limitations of current robotic policy learning methods that this paper addresses?
Current methods often suffer from severe data inefficiency and a lack of generalization. They typically train a model for a specific robot, task, and environment, requiring extensive data collection for each new scenario. This is costly and leads to overfitting, hindering the ability to transfer learned skills to new situations. This paper aims to overcome this limitation by leveraging heterogeneous pre-training across a wide range of robots, tasks, and environments.
The paper introduces heterogeneous pre-trained transformers, HPT. Can you elaborate on the architecture and how it addresses the heterogeneity problem?
HPT employs a modular architecture consisting of three main components: embodiment-specific stems, a shared transformer trunk, and task-specific heads. The stems act as tokenizers, mapping diverse sensor inputs, proprioception and vision, from different robots into a shared latent space. The trunk, a shared transformer network, processes these tokens to learn a task and embodiment-agnostic representation. Finally, task-specific heads map the trunk's output to the appropriate actions for each task. This modularity allows the model to handle the vast heterogeneity inherent in robotic data.
The paper emphasizes the importance of scaling. What scaling behaviors did the authors observe, and what factors influenced the performance?
The authors investigated scaling along three axes: data, model size, and compute. They found that increasing the amount and diversity of training data, along with increasing model size and compute, led to improved performance up to a point. However, simply increasing data without sufficient compute could lead to performance plateaus. They demonstrated this by pre-training on up to 52 datasets and a model with over 1 billion parameters.
The use of 52 datasets is impressive. Can you describe the diversity of these datasets and the types of data included?
The datasets encompassed a wide range of sources: real-world robot teleoperation data, simulation data from various simulators, MUJOCO, Drake, PyBullet, etc., and even human video data. This diversity in embodiments, tasks, and environments is crucial for learning a generalizable representation. The inclusion of human video data, while lacking proprioception and action labels, provided complementary information, demonstrating the flexibility of the HPT framework.
How did the authors evaluate the effectiveness of HPT? What metrics were used, and what were the key findings?
The evaluation involved both pre-training and transfer learning. Pre-training performance was assessed using validation loss, a common metric in large-scale pre-training. Transfer learning was evaluated using task success rates on unseen tasks in simulation and real-world benchmarks. HPT consistently outperformed baselines, demonstrating significant improvements in both pre-training and transfer learning performance. Improvements of over 20% on unseen tasks were reported.
The paper mentions several related works. How does HPT compare to existing approaches in robotic policy learning?
HPT distinguishes itself by its ability to handle broader heterogeneity, including both proprioceptive and visual data, unlike many previous works that focus primarily on vision. It also explores scaling behaviors at a larger scale than previous studies, using more diverse datasets and larger models. Furthermore, HPT's modular architecture offers greater flexibility in adapting to new embodiments and tasks.
The paper highlights the challenges of real-world evaluation at scale. What were some of the limitations of the real-world experiments, and how could these be addressed in future work?
Real-world experiments were limited by the number of tasks and embodiments tested and the relatively short horizons of the manipulation tasks. Future work could address this by expanding the scope of the experiments to include more complex, longer horizon tasks and a wider variety of robotic platforms. Furthermore, more sophisticated evaluation metrics beyond simple success rates could provide a more comprehensive assessment of policy performance.
What are some of the key limitations of the current HPT approach, and what are promising avenues for future research?
Limitations include the relatively simple embodiment splits in the dataset mixture, the lack of extensive data filtering, and the focus on supervised learning as the pre-training objective. Future research could explore more sophisticated data curation techniques, alternative pre-training objectives, example, self-supervised learning, and more complex network architectures that incorporate embodiment-specific information. Investigating the scaling laws in more detail and exploring the use of larger models and more compute would also be beneficial.
The authors mention the potential for incorporating additional modalities beyond vision and proprioception. What are some examples and how could they enhance HPT?
Additional modalities like tactile data, 3D point clouds, and language instructions could significantly enhance HPT's capabilities. Tactile data could improve fine manipulation skills, while 3D port clouds could provide richer scene understanding. Language instructions could enable more flexible task specification. Integrating these modalities would require careful consideration of how to effectively fuse and process the diverse information.
The paper concludes by emphasizing the need for more high-quality, diverse robotic datasets. What are the key characteristics of such datasets, and how could they contribute to advancing the field?
Ideal datasets would include a wide range of embodiments, tasks, and environments, with high-quality annotations and sufficient data for each scenario. They should also be carefully curated to ensure data quality and consistency. Such datasets would be crucial for training more generalizable and robust robotic models, accelerating progress in the field.
The open sourcing of the code and weights is a significant contribution. How do you see this impacting future research in robotics?
Open sourcing the code and weights allows other researchers to build upon this work, facilitating collaboration and accelerating progress. It enables reproducibility and allows for further exploration of the HPT architecture and its potential applications. This transparency is crucial for fostering innovation in the field.
The paper mentions the use of a balanced weight sampling method during training. Can you elaborate on why this is important in the context of heterogeneous datasets?
Balanced weight sampling prevents larger data sets from dominating the training process, ensuring that the model learns effectively from all embodiments and tasks. Without balanced sampling, the model might overfit to the larger data sets, hindering its ability to generalize to other scenarios. This is a common practice in multitask learning to ensure fair representation of all tasks.
The paper discusses the use of Huber loss for action regression. What are the advantages of using Huber loss compared to other loss functions like mean squared error, MSE?
Huber loss is less sensitive to outliers than MSE. In robotic data, outliers can arise from various sources, such as sensor noise or unexpected events. Huber loss mitigates the impact of these outliers, leading to more robust training and improved generalization. It combines the benefits of both L1 and L2 loss functions, providing a balance between robustness and smoothness.
The paper mentions the use of a cosine learning rate schedule. What is the rationale behind this choice, and how does it contribute to the training process?
A cosine learning rate schedule gradually decreases the learning rate during training, following a cosine function. This helps to stabilize the training process and prevent oscillations, allowing the model to converge to a better solution. The gradual decrease in learning rate allows the model to fine-tune its parameters more effectively in the later stages of training.
The paper explores different head architectures, including MLPs and diffusion policies. What are the trade-offs between these choices?
MLPs are simpler and computationally less expensive, but may not capture the complex relationships between actions as effectively as diffusion policies. Diffusion policies, while more complex, can model the stochasticity of actions and potentially lead to more robust and flexible policies. The choice depends on the specific task and the desired level of complexity and performance.
The paper discusses the modularity of the HPT architecture. How does this modularity contribute to its flexibility and adaptability?
The modularity allows for easy swapping of different components, such as stems, trunks, and heads. This flexibility enables the adaptation of HPT to new robots, tasks, and environments with minimal changes. Researchers can easily experiment with different architectures and pre-trained weights for each component, optimizing the model for specific applications.
The paper mentions the use of pre-trained vision encoders. What are the benefits of using pre-trained encoders, and how do they contribute to the overall performance of HPT?
Using pre-trained encoders leverages the knowledge learned from large-scale image datasets, improving the model's ability to extract meaningful visual features. This reduces the amount of data required for training and improves the model's generalization capabilities. It also speeds up the training process, as the encoders do not need to be trained from scratch.
The paper highlights the importance of handling missing modalities. How does HPT address this challenge, and what strategies could be employed in future work?
HPT addresses missing modalities by using a modular architecture that allows for flexible input configurations. If a modality is missing, its corresponding stem can simply be omitted. Future work could explore more sophisticated techniques for handling missing data, such as imputation or learning to predict missing values. This would improve the robustness of HPT to noisy or incomplete data.
The paper discusses the potential for using larger models and more compute. What are the expected benefits of scaling up HPT, and what are the potential limitations?
Scaling up HPT is expected to improve its generalization capabilities and allow it to learn more complex relationships between sensor inputs and actions. However, scaling up also increases the computational cost and requires more data. There's a trade-off between the benefits of increased capacity and the costs of increased resources. Careful consideration of the scaling laws is crucial for efficient scaling.
This has been a thorough discussion of the paper. Thank you for your insights.